let's try to discuss about frequency modulation. Before going into discuss about that topic, let's try to see what are the problems related to amplitude modulation. Now, in the case of amplitude modulation, amplitude of the carrier wave was changed according to the message signal, but noise can be easily added and change the amplitude of the modulated signal. Now, in the case of amplitude modulation, if this was our modulated wave, and if there is a presence of noise like this kind of signal, then it can be added with this signal and it can affect the amplitude of this wave and it can cause distortion. As the varying amplitude contains the actual information, so the change of amplitude may lead to the loss of information. So what we can do now? We need to find out some other way where the change of amplitude is not desired. So how we can achieve such a thing? Before going into see that, let's try to see what are the parameters of a wave. Here you can see that I have taken a cosine wave which has three parameters. One is amplitude, another is frequency, and phase. Now, in the case of amplitude modulation, we were changing the amplitude of the carrier wave to capture the message signal. But amplitude modulation has a disadvantage that noise can affect that modulated signal which contains the information. So if we try to vary one of these two parameters, then the presence of noise cannot exchange the original information contained by the modulated signal. So that's why we will be using any one of these two techniques. So we can this two actually called angle. So if we change one of these two quantity, then it will be called angle modulation. So in this video I will be talking about frequency modulation. Before talking about frequency modulation, let's try to see the waveform of frequency modulation, because it will make much more sense. Now here I have taken a sine wave and a high frequency carrier wave. Now how the wave will look like after frequency modulation? Now, as I have told you that in the case of frequency modulation, the amplitude will remain constant, rather the frequency will be changed to capture the message signal. So after modulation you will be seeing that sometimes the frequency will be increase, sometimes decrease, and in this manner. Okay, let's try to see. Now I have drawn all of these halves, so you can see that at this half amplitude of the modulating signal is increasing, so the frequency should have to increase at this period of time. Here you can see that the frequency is increasing, and after this half, means in this half the frequency is decreasing, the amplitude is decreasing, so the frequency should have to decrease in this way. And after this half, in this half the frequency is further decreasing and going to the negative maximum, so it should also decrease. But after this, in this half the frequency is increasing, so the frequency should increase again, and in this half the frequency is increasing, so the amplitude is increasing, so the frequency should have to increase. So the frequency modulated wave will look like this. Now let's try to derive some equation for frequency modulation in order to achieve this thing. Let's try to assume that our message signal is given by mt. I am taking mt as am cosine of omega m t. It can also be written as am cosine 2 pi fmt, because omega m is the angular frequency and fm is the actual frequency. So relation between angular frequency and actual frequency is omega m is 2 pi multiplied by fm. Now I need to take a high frequency carrier. So let's take a carrier wave as ct. So it will be AC cosine omega ct, and obviously omega c is greater than omega n, or we can say that 2 pi fc is greater than 2 pi fm. Now I will be assuming some equation before deriving the equation for modulated signal. Modulated signal, let's say it is st. So st will be given by, as I have told you that amplitude will not being changed in the case of frequency modulation, so it will be same as the amplitude of the carrier. Now this term omega c will be changed, so I'm calling this as theta. What is theta? Theta is the changed frequency. Now let's say that the instantaneous frequency of modulated signal is omega I. Why I'm saying instantaneous frequency? Why not frequency? Because as in the case of frequency modulation, the frequency will be changed according to the message signal. That's why it is a varying quantity. So in the case of varying quantity, we will use the term called instantaneous, because we will get different values of that term in different instance of time. So what should be the value of omega I? Omega I will be 2 pi of fit. Fi is the actual instantaneous frequency, and omega I is the angular instantaneous frequency. Now so we can write omega I as d theta of dt. Now we can write theta as 2 pi of fit. Now if we differentiate this theta with respect to time, you will get that theta is 2 pi fit, and d theta will be 2 pi of fit into dt, and theta will be integration of fi from 0 to t dt. So this is the expression for theta. Now we need to find out the expression for fi. So in the case of amplitude modulation, the instantaneous modulation we can say also in this way, but the modulation of the modulated signal was changing according to the message signal. So here something should be added with the frequency of the carrier. So what is that thing? That thing is kf into mt. So this is actually changing according to the message signal. Kf is the frequency sensitivity. We can take it as 1. So this is the equation. Now if we put this equation here, you will get that theta equals to, I'm just putting the value of fi in this equation. You will get that fc plus kf into mt, kf multiplied by mt multiplied by dt. So this is the equation for this is the expression for theta. Now as we have said that st was ac cos theta, so the final equation for the modulated wave will be st is given by ac cosine of the value of theta, which is 2 pi integration of 0 to t fc dt plus 2 pi kf integration of 0 to t, integration from 0 to t of mt dt. I am just separating the terms. So this is the equation for frequency modulated wave. Now we need to expand this equation further. Before expanding this equation, I would like to introduce another term called frequency deviation. As you can see that the frequency of the carrier wave was changing, so we need to find out something called frequency deviation. Let's try to see what is it. Frequency deviation is the difference between the maximum instantaneous frequency and the normal frequency. As we can see that Fi is given by Fc plus Kf into mt. So I'm just putting the value of mt here. You will get that Fi is Fc plus Am multiplied by Kf multiplied by cosine of omega t. So what should be the maximum value of this instantaneous frequency? This will be maximum whenever this term cos omega mt is 1. So the maximum value will be Fc plus Am multiplied by Kf. So as I have told you that the frequency deviation is the difference between instantaneous frequency and the normal carrier frequency. Here the maximum instantaneous frequency is Fi max and the carrier frequency is Fc. So this difference will give us the del f, which is the deviation. So del f is given by Fc plus Am multiplied by Kf minus Fc, which is Kf to Am. So from this deviation we will be finding the modulation index or the modulation depth. I will be deriving that term very soon. Now let's try to expand this equation further. I'm going to put the value of Kf that we can find from this equation. Kf will be del f divided by Am. So I need to integrate this. So cosine of 2 pi Fct, I'm just integrating this term, plus 2 pi Kf is del f by Am, and the integration of our message signal was a cosine wave, so integration will give us a sine wave. So let's try to write the equation. Am cosine of omega m, or we can write at 2 pi fm t multiplied by dt. So the integration will give us this result. Two pi del f divided by Am. The integration will give us Am sine of 2 pi fm t divided by 2 pi fm. So this 2 pi and this Am will be cancelled out, and this term will be remaining term. Del f divided by fm sine of 2 pi fm t. So this is the equation for FM modulation. Now what about this term del f divided by fm? This term is called modulation index. Modulation index, or the depth of modulation. We can write it as beta. So depending upon the value of beta, the frequency modulation is also divided into two types. One is narrowband frequency modulation, another is wideband frequency modulation. So the final equation for ST will look like this. ST is given by AC cosine of 2 pi FCT plus beta of sine of 2 pi FMT. So this is the equation for frequency modulation.